Actually, thank you. Okay. So we'll now start on some of the math behind black holes. Um, okay. So first, I'll mention some of the important quantities. Okay. So here, m is the mass of a black hole. Kappa is the surface gravity. Which is the acceleration at the horizon as seen at infinity. This is okay. Yeah, you have to actually do an example to see what this means, kind of. Yeah, other way, I mean, well, anyhow. A is the area of the event horizon. Okay. So, Tasnava showed you the solution for a spherically symmetric black hole, right? So she showed you she derived this black hole. Okay. So we're going to use the signature of minus plus plus plus. Does everybody know what I mean by that? Yeah. So this is the signature. So that means our line element is ds squared minus 1 minus. Okay, so I'm here setting g is equal to 1 over r dt squared plus dr squared 1 minus 2m over r plus r squared d omega squared. So here, does everybody know what d omega means? D omega so this is like this is the solid angle. So this d omega is a change in solid angle. Okay. So if you're on if you're moving radially, then none of your angles are changing, right? Moving in the radial direction, then this is 0. Okay. Then you just have this part, this. Okay. Yeah. So here, d omega is like, okay, so it's whatever d theta squared plus sine squared d phi squared. Okay. So as I said here, we're setting G1. We're also setting speed of light is equal to 1. So this is our convention. People always do this, and then it's a little bit confusing when you want to put all the units back or all the constants back in. So here, things to note. The things to note. When r is equal to 2m, look what happens to this coefficient. So this is G00. Okay. So when we write this in terms of the metric tensor, this is G mu nu dx mu dx nu. So when it's dx0, meaning dt squared, then this is G00, right? So when r is equal to 2m, G00 is equal to 0. Okay. And that means, and also GRR, which is this term. Well, this is 1 minus 1, 1 minus, I mean, it's like, this is 0, but you're dividing by 0. So in the physicist language, GRR is infinite. Okay. Or at least the sign of, okay, the absolute value of it's infinite. Now, the fact that this whole thing disappears, okay, might think you that, okay, there's something wrong with the metric. Something is breaking down. The system is breaking down. That turns out to be a coordinate singularity, not an actual singularity. So G00 being 0. Now, when your metric, okay, so one like G00 being 0 means that changes in dt don't lead to anything, right? Okay. So you might think, okay, something is wrong with my distance formula. I mean, it's like a distance formula, okay? But what that just means is we have, okay, so I'll show you how to deal with that. So G00 being 0, that's a coordinate singularity. Okay. So this is at r is equal to 2m. But at r equals 0, you will find, okay, not a coordinate singularity, but you'll find an actual singularity. So you find a curvature singularity. So one of the ways people calculate or determine whether a curvature, whether there's an actual singularity, is they calculate like something like r mu nu lambda rho, r mu nu lambda rho, and this is equal to 12 whatever r squared over, this is the okay, well, right here, 2gm squared over r to the 6th power. So when r goes to 0, this curvature invariant, okay? So if you do a coordinate transformation, this stays the same. This blows up. So this, I think, is called the Krushman scalar or something like that. Okay. Now, in general, okay, let me just say one thing. What does it mean to have a singularity? I mean, naively would think having a singularity means stuff kind of like, I don't know, it's like blows up or something, right? But mathematically, we will say that we have a singularity when, let's say you have a, so you're moving on a curve, right? You have a path, right? And then let's say this path is whatever, parameterized by some parameter lambda. Okay, let's say it's an affine parameter, so you can add them, whatever. So that means you cannot, a singularity means that if you go along this, let's say, geodesic path, it stops at some point. Okay, you cannot extend it beyond some lambda, let's say lambda naught or something like that. So whenever your geodesics kind of like stop, okay, that's a singularity for us. So geodesics, I mean, you know that they're like the analogs of straight lines. If you're going, I mean, if there's no gravity or anything like that, there's no forces on you. If you move in a straight line, then you keep going on a straight line, right? But if suddenly you stop, that means there's a wall or something, right? I don't know. Okay, maybe it's okay. So your geodesic stops. Okay. Okay. So now let's talk about some different coordinate systems. Let me. Is it okay if I erase this part? Yeah. Question? Huh? When it's at some point, you can extend your affine parameter beyond some value. Are you saying? I couldn't hear you actually. Yeah. Yeah. You can't extend. Yeah. But it's not a weird parameter that, like, I mean, like it's like what we call a kind of a normal parameter. Okay, meaning like it's not linear. Like you go here, it's lambda. It's not increasing non-linearly. Do you know what I'm saying? And okay, I won't confuse you. Um, let's say like this part is delta lambda, lambda equal 1. This part is 1. You can't say it's something that if this is like 1, then 1. Okay, I don't want to confuse you. Anyhow, it's just it's just a place where you just stop basically. You can't extend the geodesic beyond that point. Okay, so um, so now let's do different coordinate systems. So now, okay, when you get to when you start doing these things, you just run into like just a large number of coordinate systems, and it can be confusing. So I'll give you some standard coordinate systems that people always talk about. And I'll explain what's the purpose of these. So let's say the first one is this Reggie Wheeler, also known as the tortoise coordinates, I think. Okay. Maybe they need it. Both in like a board in the space. Are they different than the one the wolves there? Okay, let's just leave it at that for right now. Okay, what we're talking. Um, so I mean, a sign of a singularity is like something, some quantity having some blowing up or something like that. Let's say that curvature invariant or something like that. Okay. Um, if you want to do surgery on manifolds and things like that, what? Okay, so let's say you have something like this. There's a singularity here. You can erase that, get rid of that. Okay, glue something else onto it to get rid of that singularity and things. Okay. But I can. There's a way to resolve singularities by kind of like cutting them away and then replacing them with other things. Um, do you know anything about Ricci flows or anything? No. Okay, so anyhow, yeah, you can ask Hasib. Hasib can tell you more about these things. Um, okay, so let's say we want to put the metric. So this is what I call the metric often. The whole line element, we often call the metric, okay? although it's actually called a line element. Suppose we want to put the metric in this type of form. ds squared is equal to some function, and then something that looks like kind of like flat space, minus dt squared plus some dr squared plus r squared d omega squared. So you know that a flat space is like this. ds squared is equal to minus dt squared plus, let's say, dx squared or dr squared plus r squared d omega squared. So this is the time in radial piece. So this looks like that, right? One is minus, one is plus. Can we do this? Well, yeah, you can do this. We can make a metric look like this in some coordinate system. Okay. And it's not hard to do. Um, so let consider a radial geodesic. Okay, so this means there's no angle change. So d omega is equal to 0. Okay. So let's say it's a null geodesic. So a radial null geodesic, that means that ds squared is also equal to 0. So that means we have 0 is equal to d. Okay, so 1 minus 2m over r dt squared plus 1 minus 2m over r inverse d r squared is equal to 0. So this means here that if you just take this to this side, take this, divide by 1 minus 2m over r, you have like this. dt squared is equal to 1 over 1 minus 2m over r squared dr squared. Okay, and this is what we're going to call dr star squared. Okay, and if you integrate this, so dr star is related to like that. So we related r star and r through this differential relation. Let's say we want to know how r star is actually related to r. Well, we can just integrate this, and then you'll find that r star is equal to r plus 2m log r minus 2m over 2m. Okay, looks okay. If you just see this formula, you might be kind of confused, but it just comes from the requirement that we want our metric to look like that. Okay. So notice here that well, r here. So r is between 2. Okay, so r here is between infinity and 2m. Let's say we take r to be between 2m and infinity, like that. Can you see this? You can. Acha. So here 2m. Okay. That's the range for r. If that's our range for r, then r star is between infinity and minus infinity. So it's kind of like stretched out this range. Anyhow. Acha. Eta. Acha. So if R star is equal to R plus 2m log what's that?
You change
Why am I taking it from 2m? You can. Okay, if let's just make it between. Let's just make it like that, okay? Well, that okay. So that it's a coordinate thing. Well, the reason why I was doing that is like we're saying, oh, okay, R equals 2m is a problem, okay? Okay. Let's consider it bigger than 2m. Okay, then it turns out this whole region, okay, maps to this. So here, yeah, you can see that R star goes to infinity when goes to infinity, right? And as this becomes smaller and smaller, as R gets closer and closer to 2m, as R gets closer and closer to 2m, this becomes smaller and smaller, becomes negative, right? Okay, wait, okay, why did I? So if R is less than 2m, actually, it won't be.
web we have a to be related intelligence. But and besides that we have to color.
If R is less than 2m, then it's not it'll be like the same coordinates. It'll be multi-valued, right? So the same R star will correspond to two different R's. So I guess, yeah, that's one. Okay. Is that okay? Yeah. Okay. Then what we usually do is we go to like kind of like light cone coordinates. Okay, so usual trick, we define like V is equal to T plus R, and U is equal to R star T minus R star. Okay, so these are light cone coordinates because, well, I mean, if this is R and this is T, okay, like when okay, so this is no, we're okay, so no, we want R star. So this is V, and then this is, oh, sorry, this, yeah. So this is V and this is U. This is increasing U, this is increasing V. So a light cone looks like this. Let's call light cone coordinates. So what? Okay, so let's. What is constant U? When constant U, okay, is when T minus R star is equal to constant. Okay. So that let's say it's equal to 0. So let's T minus R star is equal to 0. That the constant in that case is 0. So in that case, T is equal to R star. So that corresponds to one value of U, right? What is this? T is equal to R star. Well, that's what this line is, right? Right? So that corresponds to U is equal to 0, right? So this means this is the V axis. And same you can do, this is the U axis. Okay? When V is equal to 0. When V is equal to 0, then T is equal to minus R star. Okay, so remembering what is V and what's U is useful. I always get them mixed up. Like, okay, somebody's talking about U and V, and I, whatever, mix V and U up. Anyhow, the reason why people like to do this is you can take a quadratic form like this, dx squared dt squared like this, and you can write it as du dv. Okay? Or vice versa, you can go from here to here, where if whatever u is equal to t minus x, v is equal to t plus x. Okay? Okay, so if we do that, what we're going to do is we're going to rewrite our metric in terms of u and v and r, actually. Okay. Okay, so let's start like here. ds squared is equal to 1 minus 2m over r. Okay. So when we use the r star coordinates, the metric becomes this. So there's this common factor outside. It's called the conformal factor. Okay. Now if I write this in terms of u and v, that becomes du dv. What I can also do is I can write that du is equal to dv minus 2 dr star. Okay. Because is that clear to you? Because like this, okay, and du will be equal to dv. You have to take minus 2 of these dr stars. Okay, so then this is equal to 1 minus 2m over r. Okay, so this is du dv. So I'll write here dv minus 2 dr star dv plus r squared d omega squared. Okay, fine. I know you're asking why am I doing this, but okay. Now this is just algebra. We have here dv squared. I'm going to take this through there. I have minus 2, 1 minus 2m over r. Dr star dv plus r squared d omega squared. Now notice here, I have a dr star and I have this thing here. But dr star was related to, this is equal to dr over 1 minus 2m over r. Okay, now let me write it out here. Well, okay. So ds squared is equal to, am I missing a minus sign? It's a minus, right? I think. Okay. Plus 1 minus 2m over r times this 2 and then this bottom factor 1 over 1 minus 2m over r. Then I have here a dr and a dv. So notice these cancel. And then I have plus r squared d omega squared. So finally, I get this form. There's a minus here. 1 minus 2m over r dv squared plus 2 dv dr plus r squared d omega squared. Okay. Now, why am I doing this? Um, so I want to show that r equals 2m is a place where you can pass through r equals 2m. So remember how we defined this singularity? Singularity is where you can't pass anymore, right? If you can pass through r is equal to 2m, then it's not a singularity. It's a kind of a harmless singularity called the coordinate singularity. Coordinate singularity means just the coordinates don't work there. You need to know it and give a different description. Okay. We used so this does this have a name? I don't know. I don't think this has a name. But we use the Reggie whatever. Reggie whatever is just so that we can write ds squared is equal to minus a conformal factor plus whatever dt squared minus dr squared. Okay. Or so this plus and this is minus. Okay. Anyhow, okay, so so we want to show that you can pass through r is equal to 2m. Okay. So let's say so consider when r less than 2m. Okay. And a radial geodesic, so d omega is equal to 0. Then using so we have here just really ds squared. I'm just going to manipulate this so that this becomes 2dr dv is equal to ds squared plus 1 minus 2m over r dv squared. So all I did was I took the ds squared on this side, and I took the essentially I took this guy, I moved it to that side. Okay. And I dropped the d omega squared because I'm saying it's a radial geodesic. Okay. So then let's just play some games. I'll factor on a minus sign. There's no minus here, so I have to put a ds minus ds squared. And so this becomes minus 1 minus 2m over r. But I'll play a little game. This minus, I'll get rid of the minus by changing this to 2m over r minus 1. Okay. And then we have dv squared. Is that okay? It's just algebra, okay? Okay, so then what's the point here? So we want to, okay. So for a time like geodesic, ds squared is less than or equal to 0, right? It's if it equal to 0, then it's null, right? So that means this is negative or whatever. It's non-positive. So that means this is positive, right? Okay. And since r is less than 2m, this is also positive, right? Okay. So that to have a positive quantity. So this is positive. This is also positive. And dv squared, well, I mean, it's a square, so it's also positive. So then this is equal to something positive plus something positive. So that means dr, 2 dr dv is oh, and then we have, okay, so there's a negative sign. So this part is positive. So if a negative of positive, so that means this whole thing is less than 0, less than or equal to 0. Okay. So the upshot of all this is that so we have 2 dr dv is less than or equal to 0. Okay. Now, so remember that when we went to light code and coordinates, this is v and this is u. Okay. So that means for positive, okay, future directed trajectory, future directed world lines, for future directed has dv is bigger than or equal to 0, right? And you're light cone, future directed means you're in this light cone, right? So that means if your v negative is going this way, it's going in the past, right? So change in v positive, meaning that's future directed. Okay, so that means dv is positive. Okay, but that means dr has to be negative. Okay, so this means dr is less than 0. Okay, so this is not really a proof or anything like this, but what this is telling you is that you can extend a path to r less than 2m. So the conclusion here is geodesics can be extended beyond r is equal to 2m. Okay, because here, okay, so we found that r for future directed world lines, dr is decreasing. Okay. So r equals 2m is not a physical singularity. Okay. It's a coordinate singularity. Okay. Now let me draw you a picture, kind of. Yeah.
We are internal to the black hole as well. And then we are telling that here is less than zero, means the distance is increasing. We just want to point to get the shape. Perhaps we can put the device the upper. Does it mean that actually if someone goes into a black hole, size will change?
The r is the radial distance from the singularity. From r is equal to 0. R is not the size of the black. Oh, this is small r. That's not the big R. Okay. So here, okay. So let me draw a picture. Okay. So let's say this is r is equal to 2m. Okay. So let's say this is the surface of our star, or actually, let's say that's the black hole. Okay. This is T. This line is r is equal to 0. Okay. So if we're a observer here, we're moving towards the black hole. Our light phones are looking like this, and here looks like that, right? Okay. This is r is equal to 2m. Okay. And here, the idea is that this is the increasing direction of v increasing. Okay. And constant v, lines of constant v are like this. Constant v. In other words, that if this is in the direction of increasing v, this is the direction of increasing u. Okay. You can do the same trick now with you. Okay. So this is incoming geodesics. You can do the same thing for a kind of like a white hole, okay, for outgoing geodesics. Okay, but we won't. Okay. Okay. Is it clear what I'm just trying to show you here is that r equals 2m is a kind of like a regular point. It's not a singular point. That you can decrease r. Okay. You can go to r less than r. Okay. Any questions? So let me give you an example of a coordinate singularity that you're familiar with. So if this is the plane, right? So this is the radial direction r, and this is theta. Okay. So then your metric is ds squared is equal to dr squared plus r squared d theta r d. Okay. So if we parameterize the plane by theta and r, right? Now at this point, this is r is equal to 0. Okay, but it has, the theta is not defined there, right? You can have theta equals 1 pi over 2 minus pi over 2, 6 pi, whatever, right? So in this case, the coordinates are not doing a good job of labeling the points uniquely. So this means a failure of the coordinates, right? So that's what we call kind of a coordinate singularity. But it's basically, it's like saying, okay, you want to dress something, okay, with some clothes or something. Those clothes are not doing a good job of fitting or describing the object, or I don't know. Okay, so you need another set of clothes to describe the whatever. Okay, so okay, think maybe a different way of thinking about it is like this. Okay, you can describe an object, let's say, with some labels. Okay, but it doesn't work for all situations. For those situations which those labels don't work, you have to use another set of labels. So those are different coordinates. Okay. Right. So if you say somebody is like introverted or extroverted, right? Well, somebody, I don't know. Okay. So, anyhow, okay. I think you know what I mean. Okay. Yeah. Right. Okay. It's just a set of labels that describe your coordinates or your whatever. When you're, okay. I think I'm gonna, by saying more, I'll confuse you more. Any questions so far? People also use like another common example is at the North Pole. Okay. So here, okay, so it's like mm, this point is not uniquely labeled by a coordinate system, which is r, theta, and phi, because this can have many different values of phi, right? You want a coordinate system have a unique values, unique coordinate values. That's a good coordinate system. Okay. So r equals 2m. Okay, I kind of like gave you a hand waving proof. It's not a harmful, it's not a dangerous point. You don't get crushed like at the center of a black hole. Okay, how long should I go to? কয়টা পর্যন্ত যাব? Oh, actually, I forgot to say one other thing. These UV coordinates, okay, where U and V are defined in terms of T and R star. So when U is a function of T and R star, and V is a function of T and R star, these are called Eddington-Finkelstein coordinates, I think. Okay. So, if we write ds squared like this, in terms of the Eddington-Finkelstein coordinates, du dv plus cos d omega squared. It's funny sometimes people, okay, so these are okay, so this has an r, and then built inside of u is there's an r star. It's so it looks like a kind of a mess, but it kind of it looks nice how it is, okay? But if you dig deep, there's an r here, there's an r star inside of there, etc. Okay, anyhow, okay, so then if we define this big U as minus e to the minus u over 4m, big V as equal to e to the v over 4m. So these are called Kruskal coordinates. And the point of these coordinates is to kind of to shrink everything. So look, do you see that like u is equal to infinity has a finite value, small u of it equal to infinity has a finite value of u, big U. Okay, right. So and the V is okay. So this is kind of doing a job of kind of taking the coordinates and shrinking them. Okay. So that the metric looks like this. Okay. I apologize for putting you through this, but this is stuff you need to, I guess, should be exposed to at some point. So notice again, it's like a du-dv. It's a quadratic, what we call a quadratic form. The picture here, the reason why we're drawing it like this is because we get 4 regions. You start out with 2. Okay, let me draw the picture first. So this is big V. This is big U. Okay. This is when R is equal to 2m. Okay. This is when R is less than 2m. This is when R is big. Okay, this is when R is bigger than 2m. This region we will call region 1. Okay. This region we call region 2. Okay. But then there's these 2 extra regions, region 3 and region 4. What we did was basically we have a we kind we so look here. Okay, so here big U should be negative, it looks like, right? This is an exponential of something. V should always be positive, right? So it looks like U should always be negative, less than or equal to 0, and this should always be positive. So that means we have use this part. P is positive. We have this wedge here, essentially, which is region 1.
T also has negative.
Yeah, it has negative U. Does it has negative V also? Okay. So these have different these are kind of like weird values of U and V. But these are what we're doing here is we're constructing these extra regions 3 and 4 and whatever through kind of like analytically continuing our coordinates. Okay. You can analytically continue if you like. Okay, so let's say, think about it like this. Okay, your coordinates are valid here, right? Okay, if you can analytically continue to here without running into a singularity, then okay, well, nobody's gonna shoot you. Well, okay. So we didn't run into a singularity. This is because R is equal to 2m here. You showed that R is equal to 2m is not a real singularity. Okay. So we found these extra regions 3 and 4. Okay. What you can show is that this region is kind of connected to this region. If we through kind of a wormhole, although I won't show it here now, but okay. These two regions are connected through an analytic continuation, same this way. Okay, so now what I want to do is I want to do what's known as a Penrose diagram from this. So this is important because Penrose diagrams will come up all the time. So the Penrose diagrams, they usually involve region 1, 2, 3, 4. Okay, so we saw that. Okay, we found extra regions here, right? Yeah.
And these transformational gamma set as a point of that completion. Just to Goodbye. You should the transformational the positive stuff.
Yeah. Um. Okay, so if we wanted a completely conformal transfer, if this is conformal in the R and T, okay, we'd like a full conformal transformation will also take out the angular piece. Okay. So now, okay, so conformal transfer. So conformal compactification. Or also known as Penrose diagrams, Carter-Penrose. Okay, or write Carter. So Carter was Professor Jane Islam's contemporary when he was one of his classmates. So we asked, I emailed Brandon Carter if he would come to the event, but I didn't get a reply. He's like 90 something years old. So I guess that's understandable. Okay, anyhow, but I should have been more aggressive. Maybe next time we'll. So here for the Penrose diagrams, what you're doing is you're bringing the whole space-time into a finite coordinate range. Okay, so in this case, we'll bring plus infinity and minus infinity to these I'll introduce these new coordinates u tilde between pi over 2 and pi over 2 minus pi over 2, and v between pi over 2 and minus pi over 2. So I'll map all the coordinates for the whole space-time into this finite coordinate range. Okay. Also, in the Penrose diagrams, I have extra regions from whatever analytic continuation. Okay. The other thing is that, yeah, I think those are the two main things that characterize Penrose diagrams. The other thing that people always say is that straight lines, okay, like lines at 45 degrees, they're light rays or they're null. Okay, so that means okay, so a conformal transformation is something which can change the size of something, but it doesn't change your direction. It doesn't change the shape, in a sense. So if you do if your light is going like, okay, so a normal space-time diagram looks like this: T and X, right? This is our light flow, right? I do a conformal transformation, or I could do let's say conformal transformation. So I compactify everything to a finite range, and I get some new, let's say, whatever, V tilde and U tilde, and this is my whole piece right here. But light rays are still going like this and like this. This is still my light phone. Okay. The shape is not different. Shape. Okay. Acha. So a conformal transformation will change. It will stretch distances. It won't change it won't change orientations. It won't change that. It won't like if this is okay. So when it's like magnifying or zooming, it's like making bigger or making smaller. Okay. Okay. So in a sense, okay, so you know how your distance L, whatever L squared is, X minus Y squared, or X1 minus X2 squared plus Y1 minus Y2 squared. Okay. So now if I say, okay, this L squared is equal to lambda squared X tilde 1 minus X tilde 2 squared plus Y tilde 1 minus Y tilde 2 squared. Okay. Then I've done a conformal transformation, right? My distances are different. So let's say I do like this, okay? And this is my new L tilde squared. Okay? My distances are different, but the actual it doesn't look different. The shape doesn't look different. Anyhow, okay. Okay, so now let's do. So I had here ds squared is equal to minus 1 minus 2m over r du dv plus r squared d omega squared. Now I do this I'm going to do this conformal transformation. U is equal to 10 U star. V, I'm going to make it 10 V star. Okay. So this means that U has this coordinate range and V has capital V tilde. Sorry, U tilde has this coordinate range and capital V tilde has that coordinate range. Okay. Now, okay, I'll see if I'll write down as much of the algebra as I can. So here, for example, du is equal to secant squared u tilde du tilde. dv is equal to secant squared v tilde. Yeah. dv tilde. Inputting these into there, you have ds squared is equal to secant secant u tilde secant v tilde squared. Okay. And then here, now here, okay, so you have, I'm including the radial piece. R squared cosine squared u tilde cosine squared v tilde d omega squared. Then I'm going to use r star is equal to 1/2 v minus u. Okay, and then if I use these formulas for u and v, I can write this in terms of sine using like that. Okay, so what that's going to allow me to, is this a, so that's going to allow me to rewrite this piece. So then I'll get d ds squared is equal to let me check something. Well, here, see, okay, so notice I have here a common factor. I pulled this whole thing out, right? So this is what I will call my conformal factor. So this is equal to ds squared times something, whatever, lambda squared times some ds tilde squared. Okay. So this is like a rescaler. Yeah. Okay. So but it depends on position. It's what this is basically. Okay. So it's whatever 1/4 cosine u tilde or some 2 cosine v tilde squared. This is equal to lambda. Or no, this is lambda squared. Okay. So then you can show, okay, I'm almost done. Okay. So then ds squared is -4 R over R star. Now, if I was to, so this is what this is. Okay. If I had been compactifying not the Schwarzschild space-time, but Minkowski space-time, okay, if then this piece wouldn't have been there. Okay. And R would be equal to R star. Okay. So if I had been compactifying Minkowski, I think then we would have had whatever. So -4 there. ds squared Minkowski -4 du tilde dv tilde plus sine squared v tilde minus u tilde d omega squared. So the black hole part is changing this coefficient and putting something there. Okay. Now what does this look like? Now this is what the actual Penrose's diagram looks like. So here, this is v tilde, this is u tilde. This is u tilde is equal to pi over 2. Okay, it cuts off here. This is u tilde is equal to minus pi over 2. This is v tilde is equal to minus pi over 2. Wait, is that right? No, this is v tilde. This is u tilde. And this is u tilde is equal to pi over 2. Now, if I continue this whole thing, it looks like this. Does that? So this is the whole region of this whole Corvette region. Okay. But when I get to here, I can't. Okay, let's see. When u tilde yeah, this diagram. Yeah. Okay, so this part isn't here because this is r is equal to 0. This part isn't here because this is r is equal to 0, but for region 3. Right. So this is region 1, 2, 3, and region 4. Okay. Let's see. Okay, so when r is equal to 0. Well, okay. Okay, so what I'm saying is that this is my full region, right? Now the gravity, the black hole part is being cut off because I have an R is equal to 0 here. Okay. And that's my Carter-Penrose diagram. Now, okay, I have to figure out why is R is equal to 0 there. Let's see. Let me remember. So that's when the internal part. Okay. Well, let me just label these things here. So this is R is equal to 2m. This is also R is equal to 2m. This is R is equal to 0. This is what we call scribe plus. This is what we call scribe minus. This is we call space like infinity, I 0. This is what we call it. This is it's labeled I plus. It's called future infinity. And this is called past infinity, I minus.